full cascode nmos inverting amplifier. Consider a common source amplifier where T1 is an nmos, Vn is provided to the gate of T1, and there is a constant current source load. Output voltage is taken at the drain of T1. Replace the constant current source by a full cascode current source as shown below. So here we have replaced the constant current source by a full cascode current source, and the output is taken from the drain of T2, which is shown here. So this represents a full cascode nmos inverting amplifier. By intuitive analysis, let us find out the gain of this circuit. The gain of a common source amplifier is given by minus Gm times Rout, where Gm is the transconductance. The transconductance of this circuit is nothing but the transconductance of the input transistor, that is the transistor where the input voltage Vin is provided. So the transconductance of this circuit is equal to minus Gm, sorry, it is equal to Gm1. What is the output impedance of this circuit? The output impedance, that is Rout, is the Rout seen at the output node, that is Vout. This is equal to Rout up parallel to Rout down. What is Rout up? Rout up is nothing but the impedance seen at the drain of T3 when T4 is present. This is equal to RDS4 times gain of T3, that is GM3 times RDS3. So Rout up is nothing but RDS4 times GM3 times RDS3. Next is Rout down. What is the Rout down seen at the drain of T2 when T1 is present? That is nothing but RDS1 times gain of T2, that is GM2 times RDS2. Here, since the bulk of T2 and the source of T2 are not shorted, there is bulk to source voltage. Therefore, a term called GMB2 gets added to GM2. So Rout down will be RDS1 times GM2 plus GMB2 times RDS2, which is shown here. Rout will be equal to Rout up parallel to Rout down. Here, let us neglect GMB2, since GMB2 will be 0.2 or 0.3 times GM2. We are neglecting GMB2, and let us assume that T2 and T3 have same or similar GM and RDS, and T1 and T4 have same or similar RDS. Therefore, Rout can be written as GM3 RDS3 RDS4 parallel to GM3 RDS3 RDS4. So Rout is nothing but GM3 RDS3 RDS4 divided by 2. When two resistances of equal value are in parallel, then the equivalent value will be R by 2. So the gain of the circuit is given by minus GM1 times GM3 RDS3 times RDS4 divided by 2, which is shown here. Next is the voltage swing. What is the voltage swing input voltage swing of this circuit. The current through T4, T3, T2 are same, that which equals to I ref dash, which is decided by I ref and the W by L ratios of the transistors T5, T4, T6, T3, T7, T2. So we have a constant current I ref dash flowing through T2, T3, T4, which flows through T1. For a constant current, there is only one value of VGS, 1. So there is only one fixed input bias voltage for this circuit. What is the voltage swing, output voltage swing? So Vout cannot go to VDD because the transistors T4 and T3 has to be in saturation. We know that for transistor T4, the gate voltage and the source voltage are same because Vx will be equal to Vy and the gate voltages are same. So voltage of gate voltage of T4 will be equal to gate voltage of drain voltage of T4. So this acts like a diode. So condition for saturation of T4 is nothing but VGS4, and condition for saturation of T3, that is equal to VGS3 effective. So Vout max will be VDD minus VGS4 minus VGS3 effective, which is shown here. So Vout max will be equal to VDD minus VGS3 effective minus VGS4. VGS4 is written as VGS4 effective plus VTH. Next, what is the minimum value the Vout can take? Vout minimum cannot be ground because the transistors T2 and T1 has to be in saturation. Here the condition for saturation for T2 is nothing but VDS should be less than VGS2 minus VTH. So VDS2 minimum will be equal to VGS2 effective. VDS1 minimum will be VGS1 effective. So Vout minimum will be VGS2 effective plus VGS1 effective, which is shown